There will be about 5 minutes for questions at the end, so hold off.
Great. Oops, let's close that down. So hi, everyone. My name is Matthew Rocklin. I work for Continuum Analytics. Continuum is a company that's a for-profit company inside the open source data science side of the Python ecosystem. So they do consulting and training and such. We also apply for grants, and those grants support open source software. Dask is one such example of that. So I work on a project called Dask, which is a library for parallel and distributed computing in Python. Talk a little bit about that, and also sort of generally about parallel computing in Python more generally. So this is going to be a combination of slides and of sort of live demonstrations if the wireless plays nicely with us. The slides are available at my webpage at matthewrocklin.com/slides/PyCon-2017 if you want, if I'm sort of boring and want to sort of jump ahead. I come from like the Numpy side of the PyCon stack. So if you're sort of, raise your hand if you're more familiar with Numpy than Django. And if you're more familiar with Django than Numpy. Yeah, that's great. It's like 50-50. This is a crazy conference. So Jake mentioned this in the beginning of the keynote today, which I loved, that we are a mixed group. This I think would be a talk about mixing a couple of those sides together. So we're going to take the sort of the networking side of Python and use it alongside the data science side of Python to make a distributed computing system. So we have this really strong analytics system in Python. There's libraries like Numpy and Pandas and Scikit-learn. They're very fast. They're very intuitive. Scientists like them. Analysts like them. They have a flaw, which that they were designed to run on a single core mostly, and on data that fits in RAM. As that is becoming less and as we're studying at larger and larger data sets and larger clusters, we now want to expand those libraries, that whole ecosystem, beyond just single core processing. And that's hard to do. So we just want to parallelize a single library. We want to parallelize an ecosystem of thousands and thousands of packages. So I'm going to steal some slides from Jake. So these are the slides Jake brought up in the keynote this morning of the Python scientific stack. And there's Python at the core. There's some core libraries on top of that, like Numpy. And on top of that, we have things like Pandas and SciPy and all these other sort of slightly more peripheral packages. And as you go out, there's actually thousands of little small packages. Packages for genomics and for people doing sequencing and people studying the sun. And there's thousands of little small research groups that are all producing software using their expertise that they have alone to support lots of scientists. These are people doing real work, helping the world. And we want to sort of parallelize not just Numpy or Pandas, but everything. And that's a big challenge. So that's sort of the challenge we're sort of faced with and are foolishly trying to solve. And these packages are also, they have custom algorithms. It's not just one kind of thing. They'll have their own secret sauce. They're made by smart people. So we need a parallel computing library that can be flexible enough to handle both the solar astronomers' work and the genomicists' work. It is familiar enough that it can be adopted by a large number of people. This is, again, a challenge. So in order to try to solve this problem, I'm talking about Dask, something that I and others have worked on for the last few years, and I hope you enjoy. So this talk will be we're going to start from sort of the more Numpy Pandas-y side. So people who are more Numpy Pandas will be sort of happier, more comfortable in the beginning. And we're going to end up more towards the sort of tornado networking concurrency side towards the end. So hopefully there's something for everyone. We're talking about first parallelizing Numpy and Pandas, which is sort of the first intent of Dask. Then we're talking about parallelizing more general code, which ends up being necessary if you want to parallelize lots of packages. We'll talk about task scheduling and task graphs, and sort of compare with other computing systems that can do this sort of thing, things like Spark or Airflow. Then we'll talk more about how Dask solves this problem. We'll finish up with some sort of general talking about Python APIs and protocols that it's useful to adhere to in order to gain better adoption. And then we'll sort of finish with final thoughts. So first, we're going to parallelize Numpy and Pandas. Who has used Numpy or Pandas? Who used Numpy or Pandas in the last 3 days? OK. So there's some familiarity. I'm glad to see that. We're talking about two submodules of Dask. So this is Dask Array, which is a multi-dimensional array composed of many small Numpy arrays. Let's say I'm looking at climate data. And I have the temperature of the Earth every square mile for the entire Earth. that might be a very large array. I might not be able to put that array inside of one computer. Instead, I'm going to block that array up into many different pieces and put them on different computers or on my hard drive. And Dask array is going to logically coordinate all of those NumPy arrays. So Dask array is a collection of many NumPy arrays. And Dask array is going to, when you type in Dask array.sum, it's going to figure out how to compute that sum by doing all this coordination with the NumPy arrays. Similarly, there's projects like Dask data frame, which is a logical connection of many pandas data frames. So for example, we might have we might have a time series, and the data for every month is quite large. That can fit maybe on one computer. We need to use many computers to store our entire data set. Or we need to use our hard drive that is for many months. So what Dask data frame and Dask array provide is they provide an interface that is very, very similar to NumPy and Pandas, but it operates in parallel, either on your laptop with many cores, scaling out on your disk, or across a cluster using many computers. Additionally, because they're using NumPy and Pandas under the hood, a lot of things work very easily with them. So it's a very sort of lightweight change to your code base. So I'm going to switch to a couple of examples. Hopefully the wireless is working a little bit better today than yesterday. I have here a cluster running on Google, Google Compute Engine. And this cluster has 32 machines. Each machine has 2 cores. And I'm going to create an array. Let's make that a little bit larger. I'm going to create an array which is 1,000 by 1,000, or 10,000 by 10,000, but composed of NumPy arrays which are 1,000 by 1,000. So there's sort of a 10 by 10 grid of NumPy arrays. Each element of that grid is a NumPy array 1,000 by 1,000. And now when I compute that on my cluster, Dask has gone ahead and has computed all those NumPy arrays for me. We've seen that here on the left. So we're going to see these plots a fair amount throughout the talk. So I have 64 cores, and they're on this axis here. So every line here is what a core has been doing over time. And we see that this core called the NumPy random function a couple of times and created a couple NumPy arrays. So on my 32 machines, I have 100 NumPy arrays in memory on them, spread around them. If I do something, let's say I'll compute the sum of this array. It's a fairly simple computation. Dask is going to go ahead and compute the sum of all the intermediate arrays. It's then going to transfer some of those intermediate values to other machines. That's the red. Red is data transfer. And it's going to compute some final result. And it gives us back a nice answer in sort of fast time. Something more complex. I'll try to scroll this down for people in the back. Do something more complex. If you sort of are familiar with NumPy, this syntax should look familiar to you. And so we can do a lot of these NumPy computations, what look like NumPy computations, but are actually spread across a cluster. So this is sort of the highest level use of Dask. It looks like NumPy, but actually runs on terabytes of data, if you wish. Similarly, we'll consider a Pandas data frame example. So here I have a bunch of CSV files on Google storage. This could be on S3 or on Amazon or as you like. And this is the New York City taxicab data set. It's around 20 gigs on disk, around 60 gigs in RAM, so it's too big for my laptop. But I can read a little bit of it with Pandas. And this shows all of the cab rides in the city of New York for the year 2015. So how many passengers were in the cab, when did they take off, when did they stop, as well as a breakdown of the fare. So it's a large time series data set, maybe like you've sort of seen before. It's sort of convenient because it's easy to understand and it's inconveniently large. So I can't read it all on one machine, but I can read it on many machines. So here, rather than use the Pandas read CSV function, I've used the Dask data frame read CSV function, which has the same API, but breaks down my computation, takes those 12 CSV files and breaks it into hundreds of blocks of bytes, and then calls the Pandas read CSV function on all those blocks of bytes. And so what you're seeing here on the left is all the machines in my cluster are busy creating Pandas data frames in their local memory. The object we get back isn't a Pandas data frame, it's a Dask data frame, which looks and feels the same. And as we operate on that Dask data frame, Dask will do the coordination to make sure all the Pandas data frames are affected accordingly. So again, Dask is sort of like a very good secretary. It's not actually doing any computation. It's coordinating many Pandas data frames to do the right computations. Because it's all built on Pandas, it looks familiar. It did all the D-type sniffing we like from Pandas, read CSV, and it runs the same way. It sort of renders the same way. It should feel relatively familiar. And this is really important if you want to get all of the people in the Python ecosystem to use it. They tend to like Pandas, it turns out. So a simple computation, we might compute the length of that data frame. And that's, that's done relatively simply. We compute the lengths of all the intermediate values. So if we sort of zoom in over here, we computed the length of this particular Pandas data frame, and it took a few microseconds. And we did that a few hundred times. And we communicated some data over to one machine, and we computed the sum. This is a very simple computation, but we could do something more complex. Here we'll see how well New Yorkers tip. So we're going to remove some bad rows. There were like some free rides in New York City, it turns out. We're going to create a new column, which is the tip fraction. So the division of the tip versus the fare. Was it a 10% tip or 20% tip? We're going to group by the hour of the day and by the day of the week, and we're going to see the average of the tip fraction. So how well did New Yorkers tip? Grouped by hour of day. And what this does, this produces thousands of Python functions that then run on our cluster, and it gives us out a nice result. So Dask data frame turned this Pandas-like computation into thousands of Python functions that had to run on all of our Pandas data frames. And then the Dask task scheduler ran all those functions for us in about like 3 or 4 seconds. We get back the nice result that New Yorkers tip relatively generously. As a recent migrant to New York, I feel now proud of this. It's about 20% on average, with a startling spike at 4 a.m. It's 38% on average tips at 4 a.m. I understand this is last call at the bars. But so, we did some data science on a large and convenient data set with APIs that we already knew on a cluster that was, relatively easy to set up. So this is sort of like the first big hurrah of Dask. Dask gives you a parallelized or distributed NumPy array or Pandas data frame. And for some people, that is useful. However, it turns out, so we thought this was useful too, and then we took it to academic groups and to companies, and we said, hey, isn't this useful? And they said, yeah, but our problems are actually a little bit more complex. It turns out that not all problems are a big data frame or a big array or a big list. Instead, people often had code that looked like this. This was just normal Python code with for loops. This is very clearly parallelizable, but it's not clearly a data frame and array computation. And so then our first approach was to sort of try to force this into being a data frame computation. Maybe sort of 2 data frames, and we're joining them and doing sort of a filter. That was an awkward process. So instead, we developed other libraries or other modules of Dask that can work on more generic code. So the system underneath Dask array or Dask data frame, system that's doing all the coordination, the secretary part, that is actually fairly flexible. And as long as we can expose that with these more flexible, more fine-grained APIs, we can parallelize far more clever and far more custom code. So this actually ends up being far more used in practice than the big data frames or big arrays, at least by sort of larger institutions. So let's see an example. I'm actually going to switch not to the cluster, but just to my local machine. This runs on a cluster just fine, but I want to show you that it is easy to use Dask on your laptop. My goal at the end of this talk is to be able to use Dask on their laptop and sort of start playing with it. So I'm going to, instead of connecting out to a particular cluster, I'm just so normally when we create a client, we'll talk about this in a little bit, we put in some address of sort of the head node of our scheduler. In this case, we're not going to add anything. That's a signal to Dask that it should create something locally. So Dask is going to create a sort of little Dask cluster on our laptop. Actually, I'm sorry, I don't want this notebook at all. I want the other one. So forget what I was just saying. So I have some functions here that simulate work. So they're going to do a small bit of work, but they're going to sleep for a while. This is maybe some code you're writing on your own. Inc adds a number, adds 1 to a number. Decrement removes 1 from a number, and add adds 2 numbers together. I can call these locally. Let's clear this out. I can call these locally, and they take a couple of seconds, probably, sort of randomly. Or I can import Dask, and I can annotate those functions to be delayed. And so what I mean here is that we're not going to, when we call that function now, we're not going to actually execute the code. So we're going to put that function and its arguments inside of a task graph that we can execute later. So now when I run that code, same code from before, it computes immediately, but hasn't actually done any work yet. Instead, it produced this object z, which holds on to a recipe of how it should be computed whenever we want it to be done. And so when I call compute on this object z, it's now going to run in parallel just on my laptop, not on a cluster, not any setup. I haven't set anything up here. I imported Dask. I called compute. By default, this ran in a thread pool, but I could run in a process pool or other things as well. But this is an interface that we can use to build up parallel computations in a sort of more Pythonic way. Now I'm going to start up a cluster, again, just on my local laptop. And one of the nice things this gives me this nice dashboard page. This is a bokeh dashboard, a bokeh web application. People are interested? That must have been Sarah Bird. There you are. Thank you, Sarah. And now we can run this on this dashboard. We can see it run. So we call decrement on one of our threads. We call increment on another thread. This little red bit is communication between two different threads, two different processes, and we called add on the results. So Dask, again, is figuring out when to call things, moving data around, doing all the parts of parallel computing you don't want to think about, while still giving you the freedom to do the things that you do. So this is neat. It becomes a lot better when you have for loops and you can make sort of arbitrary complex things. So here I've got, I'm doing lots more computations and we're filling up these processes and they're doing lots of work. I'm noticing from these progress bars it's going to take a while. So I'm going to start up some more workers, pointing it to this scheduler. So this is making 10 processes. Each will have four threads running. Those are connecting up to the scheduler, and now we're seeing that Dask is sort of responding to that. It's parallelizing nicely. I could remove them. Dask is resilient. It can scale. It can do all the nice things you want a cluster to do. So now that we have this ability, let's do something a little more complex. So we have all these numbers across all these different processes on my laptop, and I want to add them together. One way to do this is just to call sum on all of them, and they would, I have to migrate to one machine and add them together in one machine. But let's do something more fancy. Let's add them up pair by pair. So take the first two, add those together. Take the second two, add those together. And so here's some Python code that does that. And this Python code isn't Dask code. It's just Python code. If you look at this for about a minute, I think you'll probably understand what it's doing. It has a list of values, and it goes through that list, and it adds neighboring pairs in that list together. And it keeps doing that while the list is longer than one. And we can actually visualize that result. I'm going to expand a little bit for a moment. Maybe you can see that. But the graph that we get, this actually is showing us the computation that we want to compute. And you can see that it is indeed producing the kind of computation that we wanted to do. It actually kind of looks like this image up here. Again, nothing has actually run yet. We've just created a recipe for how to do these things. And if we go ahead and we ask Dask to compute that result for us, it's going to use our cluster, use all of those processes to do that. You see it's communicating between processes when necessary. At the beginning, there's lots of work to do, because we're at sort of the base of this tree. And towards the end, as we have sort of fewer and fewer adds to do, there's only a few. So if you come to the Continuum booth, I'll give you this demo. And this demo is demonstrating two things. One, big data frames. But two, the ability to write your own Python code and parallelize it. That ends up being a lot more attractive, or a lot more pragmatic. So let's go back to slides. OK, so let's dive a little bit deeper into what Dask was doing. Let's explain task graphs. Let's explain task scheduling a little bit. So Dask does two things for you. One, it produces task graphs. So you write some data frame code, and it figures out a recipe for how to actually execute that code. Two, given such a graph, and a cluster or a laptop, it figures out how to execute that graph in parallel. Those are two very different problems. Generally, Numpy, Pandas kind of people like the first kind of problem, and sort of tornado, async concurrency people like the second kind of problem. But there's sort of two things happening at once. We're talking about the first part and then the second part. So task graphs. Is this font visible in the back? Yeah? No, someone's saying this. Does this mean, yes, it is visible, or make it bigger? It's good, excellent. Oh no, I'm seeing some bads. Okay, let's see what we can do. Reveal is not, there we go. A little bit better, hopefully? Okay, I think that's probably about as good as I can go. I'm gonna we're going through a very simple array computation, and we're gonna see how Dask is turning that array computation into a task graph. So I'm creating, with NumPy, I might create an array of 15 ones with the NumPy ones function. It produces a result like that. Let's say that I only have like 20 bytes on my computer and I need to split this up between many computers. Then I might use the Dask array ones function. So we're still creating an array of 15 ones, but we're chopping it up into 3 arrays. Each array is of chunk size 5. So we're calling the NumPy ones function 3 times and producing 3 NumPy arrays. Now if I were to call something like sum on that array, Dask will know I've got to call sum on all of the NumPy ones function arrays, bring all those sums together, and compute the sum on all of them. Sort of a very simple sort of MapReduce-y kind of computation. So we're seeing NumPy-like code produce task graphs. Now this becomes more interesting if we go to 2 dimensions. So I'm creating a 15 by 15 array that's composed of NumPy arrays of size 5 by 5. So I've got 9 blocks. If I sum along one axis, I get sort of the same summing behavior. This is, again, something you could do with MapReduce, with Spark. This is sort of an easy computation to do. NumPy array computations actually become significantly more complex pretty quickly. So I'm taking that array and I'm adding it to its transpose. And so, NumPy people will be interested to see that there's, on the on diagonal, nodes only talk to themselves, and the off diagonal, they sort of talk to their transpose neighbor. And this difference is actually where, I'll get to this in a bit, but this is where old systems like, or more database systems like Spark or Storm started to fall down, when they started losing these symmetries. Dask ends up being very good when you break down symmetries. It handles generic cases. Something more complex, sort of matrix multiply. Let's subtract off the mean. Let's take the standard deviation. And we can keep going. This is actually a very, very simple thing to do. If you look at, say, the climate scientists, they do things that are 10, 100 times more complex than this. They produce graphs with millions of nodes. So we've made this graph. And now let's go ahead and compute it. So again, whoops. That's not copying at all. Nope, okay. Import Dask array as DA. So this object, y, is still lazy. We haven't actually done any work yet. Now when I call y.compute, let's time that, the answer is 0. I had a constant array, did a bunch of stuff to it, took a standard deviation. It's not surprising that the answer is 0. What's interesting is that it returned the answer in about 47 milliseconds. And in that time, 4 threads, because I have 4 cores, went through every circle in this task graph, ran that function, hold on to that result, passed it to other functions, ran those functions, deleted the results it didn't have to do, and proceeded through that graph. And so that's roughly what a task scheduler does. It has to execute this graph and give us a number back, ideally in a short amount of time. We're sort of supporting interactive people who are sitting at the computer, typing at it, waiting for a result back. So we want to be very fast. What's going on here? 1 second. Great. So systems like Dask Array or Dask Data Frame produce task graphs like this one. This is actually from a Scikit-learn computation. And then a scheduler executes that graph in parallel. So here's a trace of a single machine scheduler walking through that graph with four threads. And this is where we sort of switch from the NumPy people to the sort of more tornado concurrency networking people. How do we run these graphs efficiently? So before we talk about how Dask does that, I want to give sort of a brief summary of other options inside the sort of Python space, sort of to motivate why we had to sort of build our own thing. So we're talking about a few systems, simple systems like multiprocessing or concurrent futures, big data collections like Spark or Storm or Flink or databases or TensorFlow, and then task schedulers like Luigi or Airflow. Let's consider map. Who has used multiprocessing before? Lots of people. Yeah, almost everybody, I'm going to claim. Who has not used multiprocessing before? Sorry to pull you out. OK. 5 brave people, and maybe some less brave people. But that's OK. So I take a function. I have a bunch of data. I want to apply the function on all that data. Multiprocessing is a very easy way to do this in parallel. Think about the pros and cons of multiprocessing. It's very easy to install. It's in the standard library and use. The API is very, very simple. It's also a very lightweight dependency. Because in the standard library, libraries don't mind depending on it. Remember, that's one of our goals. We want to build a library that many libraries in this ecosystem, all of these and all the thousands more, are actually willing to depend upon. They're actually willing to put it in the requirements.txt file. Some cons. There's some cost to moving data across a process. That is unfortunate. And it's also not able to handle more complex computations. So all those graphs that we had, map can't easily do those. So let's go to something more complex. Let's look at big data collections, things like Spark or a database. So these systems are a big step up. Right? They give you a fixed API, things like map and filter and group by and join. And they let you use all of those operations, not just map, and they will handle the parallelism for you. And so this allows you to parallelize a much broader set of applications. In particular, many of these were implemented for sort of ETL, or sort of data extraction and cleaning, or database computations, or some sort of lightweight machine learning. And so using these systems, you can do all of those things. So you're given a broader set of API to work with, like the SQL language. It scales nicely, and it's widely trusted by enterprise. So I'm going to sort of take off my open source community hat and put on my for-profit evil hat. I also Dask is open source and free and everything, but it's nice to pay developers to do this. And the more people we get using Dask, and we can convince people to help us pay developers to work on it to make it better. So I actually care about this a little bit. I'm a little bit evil, and I apologize for that. Okay. So some cons about these systems. They're somewhat heavyweight. So it'll be sort of hard to convince libraries to depend on Spark. There's sort of this big sort of transfer of, you sort of have to step into the Spark world for a bit, do some computations, and then step out. It is unpleasant for a few reasons. It's focused on the JVM. Python is sort of always a second-class citizen. This is true with actually most of the parallel computing libraries out there. Storm, Flink, they were built out of the sort of the JVM stack and were sort of piggybacking on their success. Also, these systems are not able to handle very complex computations. Now, what do I mean by that? I mean the graphs that we saw before, right? These sorts of these graphs without much symmetry, right? Sort of arbitrary task graphs, where every circle in here is one Python function to run on one piece of data. So they're not able to handle these. Systems like Spark databases tend to be good at mapping a function across many things, doing sort of all-to-all shuffle communications, reducing things, but always sort of in lockstep. It's not as sort of fine-grained or granular as we need to do some of these more complex computations that we need to handle in order to support all of these libraries. However, there are some libraries that do handle more messy computations. These are systems actually commonly used in sort of the data engineering space. Libraries like Airflow or Luigi or Celery. Who in the room has used one of those libraries? Okay, that's actually awesome. That is not the case in the SciPy or PyData talks or conferences. So these libraries are able to handle much more complex, much more arbitrary task graphs. They sort of fit the model that we need. They're also Python native often. So these are libraries that we can hack on, that our communities are willing to depend upon. They're nicer in that sense. However, there are some cons. So there's no interworker storage or communication. Latencies are relatively high, so 100 milliseconds between tasks is an okay thing for these libraries. It's not okay for us. We work on sort of the millisecond to 100 microsecond level. We're not optimized for computation. That being said, they're optimized for lots of things that Dask doesn't do. I don't mean to sort of besmirch either of these libraries. Both Spark and Luigi and Airflow do lots of things that Dask won't do, but Dask is sort of good at this sort of mixing between them. So we want a task scheduler like Airflow and Luigi, but that is more computationally focused, like something like Spark or Flink or TensorFlow. And that ends up, so our sort of attempt to build that system is called Dask, so we've seen Dask Data Frame and Dask Array, and those are things built with Dask. That is not Dask. Dask is a dynamic task scheduler at its core. So it gets a graph of tasks, such as you would give to Luigi in a complex case, and it executes them on parallel hardware. Or it might be your laptop, or it might be a cluster. We're relatively fast in various ways. We're not as fast as MPI, but we're sort of faster than most other things. It's also lightweight. We'll see that in a bit. And it's well supported. So I'll talk a little bit about task schedulers. There are two main task schedulers within the Dask sort of world. There was one that was built many years ago for single machines. This typically runs on top of a thread pool or a multiprocessing pool. And this runs with very low overhead. It actually only depends, so it's about 50 microseconds per task overhead. It's fast. It can handle arbitrary graphs. It's relatively concise, about sort of 1,000 lines of code. It actually depends on nothing except for the standard library. So even very conservative libraries are willing to depend on this code. It is very, it's been stable, hasn't been changed much, and people have not wanted to change this code for a long time. This is a stable code. It is lightweight. It is easy to use. And it's used by many groups on many different applications. The diversity of applications on these schedulers is very broad. So it's likely that if you have a different application, it will also likely work. They're not optimized for like array computing or for data frame computations. They're optimized for general computing. Maybe like a year and a half ago, we started building a distributed cluster scheduler, which is more sophisticated, but also a bit more heavyweight. This is a Tornado TCP application. It's a little bit less concise. It's fully asynchronous, so you can submit graphs to the thing, even as it's running, you can get sort of a constant conversation back and forth. It supports sort of the HDFS space, the Hadoop space, and it also supports the more sort of traditional cluster HPC space. So when we were seeing things running on cluster, we were running this distributed scheduler. How it is organized, there is a single process running somewhere on your cluster, which is the scheduler. So we might call this like the master or the head node. This process is going to coordinate all of the other processes in your cluster. There are then many workers that will take instructions from that scheduler. So the scheduler might say, hey, worker one, I want you to compute this task. The worker will compute that task and hold on to the result and inform the scheduler that it's finished. The workers will communicate peer-to-peer to share data around, so they're not communicating through one central bottleneck. And then we, as a client down here, from our, maybe from our Jupyter notebooks or from some script we're running, nightly or whatever, we're then going to submit graphs up to that scheduler. So the workers and the schedulers are all TCP servers. And they're communicating over various interesting protocols. And the client is just a client up to the scheduler. So you can set this up relatively easily. You can install it on your laptop, like I did before. You can run it on a cluster. It's relatively lightweight also. So at the bottom, I'm actually just running it inside of one process. And I can start this up, including the fancy dashboard and everything, in around 43 milliseconds. So you can import this, you can run it, you can tear it down, and it is not a big thing. It is cheap. You should not think of distributed computing as being like a faraway, hard thing to do. It is like this is faster than importing pandas. Importing pandas takes like 200 milliseconds. So you should think of this as being a cheap thing to do. You can also, if you don't like Conda, you can pip install Dask. Everything is pure Python. So I'm going to go through, in the interest of time, I'm not going to go through this. But this shows sort of an example of how the scheduler might work in a simple example. So Dask is easy to use and adopt. You actually already know a lot of the APIs that Dask presents. There's no single Dask API. We largely steal the APIs of other languages, of other projects. And you probably already have the dependencies installed. You probably have Tornado installed. You probably have message pack installed. If you want Dask data frames, you need pandas, but you probably have that installed if you want that anyway. So in order to improve adoption, in order to sort of reduce the amount of creativity we had to have, Dask largely uses existing Pythonic APIs. So we support a lot of the Numpy and Pandas APIs and protocols where they exist. We support PEP 3148, which is concurrent futures. If you're familiar with that library, Dask supports that perfectly. We also do async await if you like concurrent async work. It also uses joblib. So you actually take existing scikit-learn code, and there's a way in joblib, which is scikit-learn's parallelism library, to hijack how it does parallelism, as you can run your scikit-learn code on a cluster. It may not work very well in all cases, but we, where there is an existing protocol for parallel computing in Python, we have usually implemented that. So you probably already know how to use Dask. You probably also, it's also very lightweight, and sort of just using existing libraries. Let's look at, yeah, we have a little bit of time. So let's look at some of these APIs. So again, we've seen, if you know Numpy, you probably know how to use Dask array. Here's an example with Scikit-learn. This came from this is an example from the Scikit-learn docs. And so we're making a pipeline. We're going to do a cross-validated grid search across that pipeline, just normal Scikit-learn code. And it takes around 8 seconds or 9 seconds. And now someone, actually his name is Jim Christ, wrote a library, Dask search CV, which is a drop-in replacement for grid search. So now when you run that, it's going to run that on our cluster. And it looks just the same. We're using all the Scikit-learn APIs. So it looks, it fits into existing workloads well. It ran faster. We also noticed there was a lot of white space here. A lot of our workers weren't doing anything. So now that we have a bit more computing power, let's go ahead and increase this a little bit. We'll increase our parameter search space. If you don't know Scikit-learn, that's OK. You should just understand that I'm increasing inputs, and we'll get more work. And it won't be slow. So now that we have more work, more computing power, we're going to sort of search this space a little bit better. And again, if you know Scikit-learn, this should have been pretty familiar to you. So a lot of the Dask work is just helping other libraries parallelize themselves using those same interfaces. Dask supports the concurrent futures interface. So here we can do the sort of executor.submit model. It's actually fully asynchronous. So as work comes in, you can submit more work in a fully real-time way, which is fun. We do things like async await. So here's a fully asynchronous thing. All the sort of Python code that you've seen, none of, except for the import Dask statement, none of the code you've seen on this notebook you would qualify as Dask code. It was all the kind of code you've seen before, but it was all parallelized in a nice way. And that's, again, sort of one of the objectives of Dask. OK, so again, at a high level, Dask gives you parallel APIs. Parallel Pandas, parallel Numpy, parallel Scikit-learn, a subset of all of those, not complete. It's also very good at parallelizing existing custom systems. At a low level, Dask is a task scheduler, which means that it runs Python functions on Python objects on parallel hardware. What those Python functions are, what the Python objects are, is up to you. It can be your own special object, your own special functions. Dask doesn't need to know what it is. It can just run it, and it will figure out where and when to run those functions. If the machine goes down, it'll bring it back up. All those sorts of nice parallelism things. OK, so I want to take a few minutes about sort of just general ecosystem comments. So I'm normally a fairly critical or sort of pessimistic person. I apologize, but I'm going to gush a little bit. So I think that the Python ecosystem is really the best place to build this kind of project. We built Dask way more easily than you would expect us to be able to. That's because of all the work that's already happened in the ecosystem. So let's look at sort of the Python's strengths and weaknesses from a sort of a parallel data analysis point of view. So Python has a very strong algorithmic tradition. All the community who was writing code with punch cards or in Fortran has moved over to Python, right? And they know how to do those things very, very well. They know algorithms very well. They have PhDs in math or something. A lot of battle-hardened Fortran code, which runs very efficiently. It uses just the best SSE2 instruction on your CPU. We also have, alongside of that, a very strong networking and concurrency stack. And it's sort of very rare to have both of those in the same language. We also are sort of very standard in teaching, so there's lots of people using Python. Weaknesses, I think, are not actually that true. People think that Python is slow. There's the GIL. Those are questions about packaging. So a few comments about this. The NumPy and the C sort of numeric stack on Python is very, very fast. It is running bare metal speeds. So here I have a 1,000 by 1,000 array, and I'm doing a matrix multiply. There's about 1 billion multiplies and adds in that computation, and we ran that in around 70 milliseconds. It's about 10 billion operations per second. If you think about my laptop only has a 2 or 3 gigahertz processor. So I'm actually doing more adds than I have cycles in my system. If you know about CPUs, that doesn't surprise you, but we're running at bare metal speeds. The GIL, people are often concerned about parallelism and the GIL. Again, for the numeric stack, this actually doesn't matter. The GIL is not a problem if you're mostly running numeric code with libraries like NumPy and Pandas and Scikit-learn. So the GIL stops 2 Python threads from operating at the same time. or two Python threads are executing Python code at the same time. But our threads are just calling out to some C function, and then they sort of wait until that function returns. So we're not actually calling Python code. We're calling C or Fortran code. So you can run Python with many threads and saturate your hardware very easily if you're using Numpy or Pandas or that sort of stack. You should use threads freely, unless you're doing Pythonic string manipulation. But use threads, just general comment. Alongside that, there's also this totally different community that's at the same time simultaneously building out a very strong and very intuitive concurrency and networking stack. So here's some code that, such as you might see inside of Dask, that does a lot of concurrent things. You might now write that with async await. In Dask, we use Tornado. And this code looks simple. It looks easy to understand, and that is actually remarkable. This would not have been the case 10 years ago. At the same time, it's also quite fast. So this is from a blog post about UV loop. Let's see if I can get that link in there. Talking about various UV loops, various event loops. And Dask is actually running on Tornado, which is way down here. But even that is running at 20,000 TCP requests per second, which is like totally fine for us. So this community is also very focused on performance, not in a numeric computing sort of way, but in a concurrency sort of way. So Python has both an excellent numeric computing stack and an excellent concurrency and networking stack, and that's actually quite rare. It's really a blessing that we had sort of those two groups of people in the beginning, and they're both in the same room together. And it's because of that Dask was actually really easy to build. So most of the work of building Dask was built 5 or 10 years ago by all of you, so I appreciate your efforts. In the interest of time, I'm going to stop, but many people work on Dask. It's not just me. There are various government organizations and nonprofits that fund Dask. We'd like to thank them as well. Just to show engagement, in the last 48 hours, these projects have mentioned or committed code using Dask. I just went on GitHub and searched for Dask. So it's sort of nice to see that. Okay, thank you.
We've got about 5 minutes for questions. So if you could line up by the microphones.
Sure. Is there a C API?
There's not a C API.
Okay,
Python or Dask is a Python project.
Okay, so let's say I have some code that it's wrapped with Swig, and it takes in a NumPy API or NumPy array. Could it also potentially operate on a Dask array and still take advantage of the functionality, or is it a complete no-go?
So Dask array does not implement sort of the NumPy low-level ABI interface.
Okay.
However, if you have a function, because Dask array is composed of many NumPy arrays, you might be able to just apply your function on all of them, depending on what your function does.
Okay, thank you.
Thank you.
In your demos, you were acting as a single client to your cluster. How does it behave if you have, say, multiple clients competing for the cluster's resources at any given time?
Yeah, so one Dask cluster can have multiple clients, and they're working on the same data. Dask graphs are a Merkle DAG. If you know what that means, you'll be great. So it can share nicely. That being said, most people who do multi-client workloads end up allocating separate schedulers and workers.
Okay, great. Thank you.
Does Dask do any optimization of the task graph? Is that a thing that is a priority for the project right now?
Yeah, so we do the kind of optimizations that are all linear in time. So the kind of things you would see in a normal compiler, but none of the complex ones. So in particular, we don't do any sort of like data frame optimizations, like reordering, because we don't, at the task graph level, we sort of already lost that information. But loop fusion, those sorts of operations we do nicely, calling the graph. Yeah.
Have you looked into, or do you do any sort of use of OpenCL or CUDA for even higher parallelization on the GPU?
No, but you can in your Python function. And then Dask can run that Python function on various machines with GPUs. So Dask runs Python functions on Python objects. What those Python functions do is entirely up to the user.
Okay.
You can annotate that certain workers in your graph have GPUs, and Dask will respect that and allocate accordingly. But we don't actually use CUDA to execute our parallelism.
Okay, thank you.
Can the schedule take advantage of any data locality? Say this node has this set of files, so...
Yes. In many ways, yes.
Is there any limitation to the work that you can do inside of the function that you're passing in if it's a custom function?
Sorry, say again, please?
Is there any limitations into what you can do inside of the function that gets passed into the distributed workload system?
Your function must be serializable with Cloud Pickle, so you can't have like locks or open files you're passing into it. Your function should not mutate state that's given to it. So we generally, to be resilient, we have to sort of assume that. You shouldn't call sysexit, but other than that, even that would be fine. Like Dask would recover from that just fine.
Thanks.
Okay, one more, and then we've got to.
How big can it scale up? Like, what's the largest cluster you've run it on? What's some supermassive workloads you've tried it against?
The largest cluster I've had my hands on is 1,000, oddly, Windows machines. The number to have in your head is that every task is about a 200 microsecond overhead inside the scheduler. So if your tasks take about 1 second each, you can saturate around 5,000 cores. Sort of the back of the envelope number to have in your head. But 1,000 is pragmatically what I've seen. I haven't actually seen someone try bigger and fail. But I assume if you had to do 100,000, we'd run into something. Thank you all for your time. To handle both the solar astronomer's work and the genomicist's work. It is familiar enough that it can be adopted by a large number of people. This is, again, a challenge. So in order to try to solve this problem, I'm talking about Dask, something that I and others have worked on for the last few years, and I hope you enjoy. So this talk will be we're going to start from sort of the more Numpy Pandas-y side. So people who are more Numpy Pandas will be sort of happier, more comfortable in the beginning. And we're going to end up more towards the sort of tornado networking concurrency side towards the end. So hopefully there's something for everyone. We're talking about first parallelizing NumPy and Pandas, which is sort of the first intent of Dask. Then we're talking about parallelizing more general code, which ends up being necessary if you want to parallelize lots of packages. We'll talk about task scheduling and task graphs, and sort of compare with other computing systems that can do this sort of thing, things like Spark or Airflow. Then we'll talk more about how Dask solves this problem. We'll finish up with some sort of general talking about Python APIs and protocols that it's useful to adhere to in order to gain better adoption. And then we'll sort of finish with final thoughts. And that's hard to do. So we just want to parallelize a single library. We want to parallelize an ecosystem of thousands and thousands of packages. So I'm going to steal some slides from Jake. So these are the slides Jake brought up in the keynote this morning of the Python scientific stack. And there's Python at the core. There's some core libraries on top of that, like NumPy. And on top of that, we have things like Pandas and SciPy and all these other sort of slightly more peripheral packages. And as you go out, there's actually thousands of little small packages. Packages for genomics and for people doing sequencing and people studying the sun. And there's thousands of little small research groups that are all producing software using their expertise that they have alone to support lots of scientists. These are people doing real work, helping the world. And we want to sort of parallelize not just NumPy or Pandas, but everything. And that's a big challenge. So that's sort of the challenge we're sort of faced with and are foolishly trying to solve. And these packages are also, they have custom algorithms. It's not just one kind of thing. They'll have their own secret sauce. They're made by smart people. So we need a parallel computing library that it can be flexible enough. So first, we're going to parallelize NumPy and Pandas. Who has used NumPy or Pandas? Who used NumPy or Pandas in the last 3 days? OK. So there's some familiarity. I'm glad to see that. Talk about two submodules of Dask. So this is Dask array, which is a multi-dimensional array composed of many small NumPy arrays. Let's say I'm looking at climate data, and I have the temperature of the Earth every square mile for the entire Earth. That might be a very large array. I might not be able to put that array inside of one computer. Instead, I'm going to block that array up into many different pieces and put them on different computers or on my hard drive. And Dask array is going to logically coordinate all of those NumPy arrays. So Dask array is a collection of many NumPy arrays. And Dask array is going to, when you type in Dask array.sum, it's going to figure out how to compute that sum by doing all this coordination of the NumPy arrays. Similarly, there's projects like Dask data frame, which is a logical connection of many Pandas data frames. So for example, we might have we might have a time series.
There will be about 5 minutes for questions at the end, so hold off.
Great.
So hi, everyone. My name is Matthew Rocklin. I work for Continuum Analytics. Continuum is a company that's a for-profit company inside the open source data science side of the Python ecosystem. So they do consulting and training and such. We also apply for grants, and those grants support open source software. Dask is one such example of that. So I work on a project called Dask, which is a library for parallel and distributed computing in Python. Talk a little bit about that, and also sort of generally about parallel computing in Python more generally. So this is going to be a combination of slides and of sort of live demonstrations if the wireless plays nicely with us. The slides are available at my webpage at matthewrocklin.com/slides/PyCon-2017 if you want, if I'm sort of boring, you want to sort of jump ahead. I come from like the NumPy side of the PyCon stack. So if you're sort of, raise your hand if you're more familiar with NumPy than Django. And if you're more familiar with Django than NumPy. Yeah, that's great. It's like 50-50. This is a crazy conference. So Jake mentioned this in the beginning of the keynote today, which I loved, that we are a mixed group. This I think would be a talk about mixing a couple of those sides together. So we're going to take the sort of the networking side of Python and use it alongside the data science side of Python to make a distributed computing system. So we have this really strong analytics system in Python. There's libraries like Numpy and Pandas and Scikit-learn. They're very fast. They're very intuitive. Scientists like them. Analysts like them. They have a flaw, in which that they were designed to run on a single core, mostly, and on data that fits in RAM. As that is becoming less and as we're studying at larger and larger data sets and larger clusters, we now want to expand those libraries, that whole ecosystem, beyond just single core processing. That